Good evening, students. So in the last class, we started on the solution of the our differential equation or the equation of motion. First, we started with the free vibration, and especially those equation of motions we could able to convert into eigenvalue problem. So we took up very general formulation for the eigenvalue problem and discuss the property of the mass, stiffness, and then today we will continue with that formulation and we'll take up some example also. This eigenvalue problem solution is very important for finding the natural frequency and the mode shape, which will be useful for finding the response of the system for a given disturbance, either in the form of some initial condition or in the form of some forcing with some frequency. So I'll continue with the formulation, and then I will take up some example, then the concept will be more clear. Even we'll see some property of the eigenvector or the mode shape, which will be helpful for us to decouple the equation of motions which are coupled, and which helps in solving those differential equations once they are uncoupled. So I'm sharing the slide now. So we were here in the last class. So we normalize the mass matrix, or we normalize the eigenvector with respect to the mass matrix in the last class, and we said this will be preferring because with this kind of normalization, the equation of motion will be simpler. So that I think through example it will be clear today. So when you can see here both the eigenvector in the prior to the mass matrix and after the mass matrix are same rth mode eigenvectors are there, and that we are equating to 1. And for each of these modes, we need to equate to get the normalized eigenvector. So if these two eigenvectors are not same, let us say if this is rth vector and this is sth vector, then we'll see that this particular property of the eigenvector, that this will be 0. So if here I'm taking the rth eigenvector, here sth eigenvector, and if we do the multiplication of this, that will be equal to chronicle delta rs. So that indicates that when r and s are same, we'll be having one value of this. If they're not same, then it will be 0. And this is basically orthogonality property of the eigenvector, and we'll prove this maybe tomorrow's class, this particular property. But as we are normalized for the same eigenvector, then it gives 1. If we have different eigenvector, then it becomes 0. This chronicle delta property is like this. When r is not equal to s, then it becomes 0. And when r is equal to s, then it is 1. So eigenvector, as we saw in the last class, that for each natural frequency there is a one eigenvector. The size of that is n into 1 size. And if we stack all such eigenvector from first mode, second mode up to the nth mode in a matrix form, then the size of this matrix will be n into n. for n degree of freedom system. So this matrix, which we will get from individual eigenvector, is called modal matrix. And this modal matrix is having importance that this can be used as a transformation matrix to transform the generalized coordinate which we have chosen to some natural coordinate transformation we will see today. So this model matrix is very important, and this can be used to transform the equation into normal modes in which the equations will be uncoupled. And these eigenvectors are actually, if we have some linear combination of these, so any general motion which is taking place of any dynamic system can be expressed as linear combination of this eigenvector. It's something like in Fourier series, a periodic function we split into cos and sine and in harmonics. So when we add up all those harmonic cos and sine terms, we get the total periodic function. So on the similar way, in the vibrations, if we have this vectors, eigenvectors, linear combination of this, that means if we multiply these with some constant and we add up, so we can get any general motion. Those constants will depend upon what kind of initial condition we are giving to the system. So that we'll see this particular concept, how any motion which is taking place in a system can be obtained by linear combination of these modes. As I mentioned, the modes are nothing but the relative displacements among various generalized coordinates. And for each natural frequency, they have a definite ratios. So that particular eigenvalue problem, which we have defined earlier, if we take, let us say, rth natural frequency and that, so omega square will take omega r value, omega r square value, and this eigenvector will be u raised to r. So this eigenvalue problem has been written for one of the mode, because when we solve this, we got the solution omega r and ur. If we substitute back in this equation, it should satisfy if it is the solution. So, and this r can take from 1 to n value. If I write this equation for r is equal to 1, I'm bringing the omega this side, so it becomes -2. So this for r is equal to 1, r is equal to 2, then r is equal to n. And these, if we combined the whole n equations, if we combine in a matrix form, so I'm keeping the right side here. So mass matrix is common. These will be within a matrix u1, u2, un from here to here, and then this one K matrix, U again there in a matrix, and this natural frequency square -2, that is or here. That means if I multiply the first this mass with this and this with this and with this, I'll get the first equation. Similarly, second term, this equation. So if we expand this, we'll get this. So that is one and same equation, only we have combined them, all of them, for r is equal to n here. And they can be written, so this whole thing can be written as u, m into u, k, this is u, and this I'm writing as omega -2 and dot, they represent that this is a diagonal matrix. Okay, so I was talking about how we can able to use the U matrix as transformation matrix. So here, this is Q is the generalized coordinate which we have chosen. We need to transform this particular equation to the natural coordinate eta, and so this is the transformation. And if we take the transpose of this using the transpose property, these two will swap and transpose of each of this will be there. When we take up the kinetic energy, so kinetic energy we have written earlier in terms of the mass coefficient and the generalized coordinate like this. So we can substitute, let us say, q dot. So q dot, if we do the differentiation of this, u is constant, differentiation will be of the eta only. So we can substitute this here. You can see q dot has been put as u eta dot. Similarly, at the before mass matrix, we have q dot transpose. So if we do the differentiation of this and substitute, so eta dot transpose u transpose. So this is the, we have substituted the q dot and q dot prime. So now this equation, kinetic energy expression, is in terms of the natural coordinates. If you see the terms within the bracket, if you see, we have defined this earlier. So if we normalize the eigenvector with respect to mass, we expect this will be nothing but a diagonal matrix. And in fact, if we normalize equal to 1, so this diagonal matrix will be identity matrix. So if this is the identity matrix, then that means if you multiply them, we'll get this. So this M matrix, if you normalize the eigenvector with respect to mass, we will get the identity matrix. So we'll get the kinetic energy expression in terms of the new coordinate system, that is a normal coordinate system or natural coordinate system like this. Potential energy, we have a quadratic form. Here also we can put the Q from here. So U eta is for Q, and then transpose of Q transpose will be this. Here also you can see that we can combine this U transpose K U in a if we combine it, we will get a diagonal term here also, using the orthogonality property I defined. So here this will be diagonal matrix, and we'll see that this diagonal matrix will be nothing but the square of the natural frequency. So this we already, okay, so this is the square of the natural frequency. All the diagonal terms will be square of the natural frequency. So now you see the previous equation. This was the original equation of motion in terms of the generalized coordinate. When we transform this, this eta double dot will be there. Then mass matrix after transformation becomes I matrix, and K matrix after transformation becomes omega square diagonal matrix. Eta is equal to 0. So now you see this is the first matrix, which is identity matrix. All the diagonal terms are 1. Here all the diagonal terms are omega square. So there are n number of equations, and all are uncoupled because there is no off diagonal terms in this matrix or that matrix. So if we expand this, each of the equations will be of this form. So this is the one of the equation, rth row. If we take out, this will be the equation, and where r can be 1 to n. So now you can see what is the advantage of normalizing the mass matrix eigenvector with respect to mass matrix. Because of that, we are getting the coefficient of the acceleration as 1. So that is something like dividing the throughout the equation by mass. So here k by n which is nothing but omega square. So that kind of term is coming here. So like here, if you divide by mass, K by M will come. That is nothing but omega square natural frequency. So this is a simple equation with no coefficient in the second derivative term of the natural coordinate. And here directly we are getting the natural frequency square. So that's why we prefer the mass normalization. If we are not doing the mass normalization, then some coefficient will come here, some coefficient will come here. So if we divide that, then again we can get back to this. So this is the, now you can see this is the uncoupled equation. All R equation, n number of equations can be solved independent of each other, and then we can go back to the transformation matrix to get the solution in terms of the generalized coordinate. So these are the natural coordinates. So natural coordinates is something like we have obtained a single degree of freedom system, you can see, but they are n in number. So earlier we had single system, here single system, and all equations are coupled. Here we have n number of equations, all are uncoupled. So this coordinate is called normal mode or normal coordinates or natural or principal coordinates. Now natural frequency is defined as this ratio. This ratio is, if you see here, this is the K matrix, and the eigenvector is pre-multiplied by transpose of the rth eigenvector, and the here post multiplied by this. Similarly, the mass matrix at the bottom. So if we are doing the normalization with respect to mass matrix, then it will be 1. If we are not doing the normalization of the eigenvector with respect to mass, then it will be having some value which we can call as MRR. Or in that case, the K will take some value KRR. But because we prefer to normalize the eigenvector with respect to mass, so this denominator will be 1. So this quantity will be this. Where so that directly we can able to get the natural frequency by stiffness matrix by multiplying and pre and post multiplied by a particular eigenvector. And you can see R can vary from 1 to n. So all the natural frequency can be obtained from here. Now this equation, the solution of this will be, because this is a differential equation of second order, will be having of this form, in which we can have CR as amplitude and phi r as the phase. So these two constants will be involved because this is a second order differential equation, and this is the solution for all the normal coordinates from r is equal to 1 to n. This constants we need to obtain from the initial condition of the problem for the free vibration. And the other form of this solution we can able to write by expanding this cost term that I am showing in the next slide. So here, yeah, so I was talking about, I will show the expansion of this in the next slide. But here, what I'm doing, this is the transformation which we used to transform the generalized coordinate to the natural coordinate using the modal matrix. Modal matrix is having n components. These are the eigenvector corresponding to each natural frequency, and the natural coordinates are eta 1, eta 2, eta n. If we multiply them, we will get eta 1 multiplied by the eigenvector of the first, second, third, like this. Because they are summation, we can put in this compact form, the summation form from r is equal to 1 to n, where eta r, and this is there. Now the eta r in the previous slide we have the solution of this form. So that can be substituted here. So the generalized displacement can be expressed in terms of the mode, the eigenvector, and this constants and the time function, harmonic function. As I mentioned, the CR and phi r are the constant to be obtained from the initial condition. We can able to expand this and simplify this equation. So this particular equation I'm expanding now, because cos can be expanded, cos omega t minus phi r can be expanded like this. And if I bring this here inside and club the constant term in one place, CR cos phi r is the constant, and this is time dependent term. Similarly, CR in psi phi is constant. So, and if I define CR cos phi as AR and this as BR, so eta r can be written in this form. So this is, again, we have basically two constants, AR and BR, which are related with the CR and phi r like this. So either we can use CR of phi r or AR and BR. Now this eta we can substitute in this particular form in the previous solution. Sorry, here I'm substituting this. So I got this. Okay, so you can see here, this is the generalized coordinate, that is the response of the system, the displacement of the various particles in the system can be expressed in terms of the eigenvector, which are r in number or n in number, multiplied by some constant and time dependency, because depending upon the initial condition, AR and BR we need to find out. So this is in a matrix form. So Q, T are n in number. So basically these are n such equations we have. So you can see that AR and BR, if we expand this from R is equal to 1 to n, we'll be having 2n such unknowns, because we have n number of differential equations of second order. Each equation will be having two unknown. So n into 2 unknown, 2n unknowns will be there, and that many initial conditions we need. So all the generalized coordinate initial conditions we need to solve this. So and depending upon the initial condition, you can see the AR and BR values will take some value, will be having some definite values, and accordingly the contribution of the various modes will be coming into picture in the actual response. So it may happen that we are given in initial condition, only one of the mode is contributing, so corresponding this constants will be present, other will be zero. So most of the response will be assembled, or it will be resembled similar to that particular mode. So this is it depends upon initial condition, how we are giving the initial condition. And if we have the forcing with some excitation frequency, if it coincides with one of the natural frequency, obviously the resonance condition will occur in that particular case. And here we can have n number of such resonance, because we have n number of natural frequencies. Okay. So now we'll take up how to actually I'm giving a method, okay, how we can able to solve the eigenvalue problem. This is especially good if we are developing some code for bigger problem, but for exam point of view, only because we'll be having either 2 by 2 matrix or 3 by 3 matrix, so hand calculation will be okay. But this is one procedure I'm explaining, and maybe in the subsequent class I will give a numerical example for this also. So here the eigenvalue problem which we obtained earlier. I'm defining now lambda is 1 by omega square. So if I define like this, because omega square was with the mass matrix, if we divide the previous expression by omega square, so 1 by omega square will be here. So I'm defining that as a lambda. Now I'm multiplying this expression by K inverse matrix. So here I'm multiplying. This I will be coming later. So if I pre-multiply this by K inverse matrix, so K inverse into KU minus K inverse M is equal to U. K inverse and K will give me identity matrix. And let us K inverse into M I'm defining as, because K inverse is nothing but the flexibility influence coefficient, and multiplied by mass I'm defining as D. So K inverse M I'm defining as D. Now because U is common, I can take out the U common, and remaining terms are here. So this is a matrix. Here it is indicating that this is a identity matrix. When I is equal to 1, I is equal to J, that means the diagonal terms are 1, the rest of the terms are 0. This is identity matrix representation. And D is a matrix which I have defined here, multiplication of the inverse K into M. So this can be fully populated matrix, but this is a identity matrix. Now, to get the eigenvalues, we need to take the determinant of this equal to 0. So if we take the determinant equal to 0, that I'm representing as delta lambda. So if we take this equal to 0, so this will be the polynomial. Basically, it will be in the form of polynomial. So here in the matrix form, it is represented like this. So we'll get nth degree polynomial, and we expect that the roots of this will be real and positive roots, because lambda r is related with the natural frequency square, or inverse of the natural frequency square. So if this is negative, then natural frequency will be complex, so that is not feasible for present case. So we expect the lambda r will be real and positive roots. So the previous eigenvalue problem I have written here for one of the mode lambda r, because here, this one, this is for general case, and then we obtain the eigenvalues, various eigenvalue. Now we are substituting one of the eigenvalue here and to get the eigenvector. So lambda is equal to lambda r we are saying, and this is the eigenvector corresponding ur. So okay, now I'm defining this as fr. The whole thing I'm defining as fr. So if I define that, so this equation will take up this form. Now the determinant of this is what? Determinant of this is nothing but the characteristic equation. If you see here, determinant of that we are representing as this. So there is a polynomial, and so now here I'm giving one method how we can able to obtain the eigenvector using the adjoint matrix. So let us say capital F. Here I'm using the small f. Here capital F is the adjoint matrix of small f matrix. So adjoint of matrix I'll define here. That is representing as capital F. And the adjoint of a matrix is having the property that if you multiply the matrix with its adjoint matrix, that will be equal to determinant of the original matrix into the identity matrix. So this is the property of the adjoint matrix. Okay, if you post multiply the actual matrix with its adjoint matrix, then that will be equal to determinant and equal to into identity matrix. But determinant of this, we are represented like this, and because we obtain the lambda r from this polynomial, if we substitute back the lambda r in this, it will be equal to 0 because that will satisfy the equation. So same thing is happening here. So this will be 0 because in that polynomial we are putting the one of the root. So once we put the one of the root, this term will be 0. So this identity matrix will become null matrix. So here what is representing? So I think in the next slide it will be more clear. So basically what is happening here, the actual matrix which we have here, the adjoint of matrix, if we are multiplying, we are getting a null matrix. Okay, so here I've defined the adjoint of a matrix A. So A is a matrix for which we want to know the eigenvector. Capital A is its adjoint. Adjoint matrix can be obtained using this. So if I want to find out the ij element of the adjoint matrix, so this is the formula from any mathematics books you can find out. So this is Mij is the minor of the A matrix. So Mij is the minor determinant corresponding to the element Aij. So Aij is, once I'm saying minor, that means I need to remove from A matrix ith row and jth row, ith row and j columns, and so it will reduce one column and one row. So determinant of that matrix is minor. Okay, so you can refer any mathematics books on how to define minor. So here inverse of the matrix is given. So this is the actual matrix which we want to find out the inverse. So F is the adjoint of that. If we divide by the determinant of that, then you can see here I'm multiplying this by identity matrix, and then if you see here I'm multiplying here I'm multiplying by the post multiplying by the FR. So FR both sides, FR here also. So this is the definition of the inverse of a matrix. So from there I'm taking a key, I'm multiplying this by the matrix itself, so that this becomes identity matrix. Because if I multiply the actual matrix with its inverse, I should get identity matrix. So if this becomes identity matrix, then this can be written as this. I'm writing in the left side, and this I'm multiplying with this. And because we know this determinant for a particular eigenvalue is 0, so we are getting a null matrix. So this is the matrix. This is the adjoint of the matrix. That is a null matrix. Okay. So the use of this will be clear through one example. Basically, what is happening here? Here we'll find the adjoint matrix will be a eigenvector of the actual matrix. So this will be clear through one example. So the idea of finding the adjoint of a matrix is that each column in this will be eigenvector of that particular mode. So here we have taken the rth mode. So that will be that particular eigenvector will be coming. If you want some other eigenvector, again we need to substitute that eigenvalue, and then we'll form this matrix. Again, we need to find out the adjoint of the matrix, and that will be the eigenvector of this particular thing. Okay, so for example, I will clear this. Before I take up example, if you have any queries, you can ask. So I will take up example, then through numerical example, I think things will be more clear. Various concepts regarding orthogonality and normalizations and okay. So I'll continue with the example. Okay, so this is one example in which two pendulums are there, and so here mass m1 is there, length and m2 is there. So this is a 2-degree of freedom system. We can choose the generalized coordinate θ1, θ2. This is the most convenient way to define the generalized coordinate for pendulum case. We can able to obtain the potential energy, kinetic energy, and even we can get the equation of motion. So this you already know how to get the equation of motion. So I'm starting with this. So this is the equation of motion and is having 2-degree of freedom system. So this is 2 by 2 matrices are there, mass matrix. Mass matrix are coupled, but stiffness matrix is uncoupled. So if we, because these are variables, so let us take some values to these mass and length. So whatever the mass and length is given, if we substitute in this for simplification, I'm taking g is equal to 10. So we'll get a equation like this, having this is the mass matrix, this is the stiffness matrix. Now to get the eigenvalue of this particular acceleration, because we want to solve the free vibration or harmonic motion, this particular acceleration will be proportional to the displacement but negative of that. So that, and the lambda is nothing but the natural frequency square. So this is the simple harmonic motion condition. So if we substitute this here in the equation of motion, we will get this. And because now is θ1, θ2 vector, they can be taken common. If we take common, this mass matrix and stiffness matrix will combine to give us this. So basically, this is the D matrix which we got earlier. I think, yeah. So this is the matrix. Now, to have the non-trivial solution, that means non-zero solution, that because this is a homogeneous equation, the determinant of this we need to equal to 0. So if we put the determinant of this equal to 0, we'll get a characteristic equation, which is nothing but the frequency equation in terms of lambda. So this is a polynomial because we have 2-degree of freedom system. So we are getting a polynomial of 2nd degree. If we have 3-degree of freedom, this polynomial will be 3-degree polynomial like that. So if we have a degree of freedom n, so degree of polynomial will be n. So here, because this is simple by hand calculation, we can able to obtain the lambda 1 and lambda 2, two roots of this polynomial. So these are the two roots of the polynomial. Now these are the eigenvalues, and how we related the eigenvalues with the natural frequency. Basically, square root of the eigenvalues for this particular case will give us the natural frequency. So if we take the square root of these two, we will get the first natural frequency 3.8 radians per second. Second is 12.8. So I put the in a particular order. The lowest one I am keeping as omega and f1, and the next higher is 12.8. So if we have 3-degree of freedom system, then accordingly we need to arrange the third next to this. So we got the natural frequency by taking the determinant of this matrix. Now the remains how to find out the eigenvector. So eigenvector is a simple method. Usually in mathematics also you use this method. So in the previous equation here, I am now putting one of the lambda value. So I'm putting the lambda 1 first, and then I'll be putting lambda 2 in the second time. So when I put the lambda 1 here, so lambda 1 is having 14.5 value. So if I put and simplify, so I'll get this matrix. So now I have already substituted the lambda 1 here and simplified. So now if I take any of the two equations, either the first equation or the second equation, so I've taken the first equation, this multiplied by theta 1 minus this multiplied by second. Now this equation can be written as theta 2 by theta 1 like this. So you can see that the ratio is 1.137. So that means if I take theta 1 as 1, theta 2 will be 1.137. So here we are getting the ratio of two generalized coordinate as some unique value. But we are not getting the unique value of individually these theta 1 and theta 2, but the ratio form. So that ratio form means the relative displacements we are getting as a constant quantity. So that is very important here. So if we have 3 degree of freedom system, so we will find that the theta 2 by theta 1, theta 3 by theta 1 will be having some fixed ratio. So that's why this eigenvector are arbitrary in amplitude, but the shape or the relative displacements are unique. So this is the so here I will put theta 1 and theta 2. So if I put theta 1 is equal to 1, theta 2 will be this. If I divide this 2 by this quantity, I can get this. So both are eigenvector of the problem. Only thing how I normalize. Here I normalize with respect to first displacement. Then I'm getting the second displacement, this value. If I say theta 2 is unit value, then theta 1 will be this. So, but both are eigenvalue for eigenvector for the first eigenvalue. So this is very important that this is corresponding to the first eigenvalue. So this is corresponding to the first eigenvalue. So here I have plotted how the relative displacement will be visualized. So I have plotted this one. So I'm giving theta 1 displacement. So this is basically angle, not the distance. Theta 1 is the angle. So the first angle theta 1 is unit. So second angle will be 1.137. So obviously it will be larger than the first one. And both are positive. That means if theta 1 is in this direction, theta 2 is also in the same direction. Okay. So this is not the distance, these are the angles. So this theta 1 and theta 2. So this is corresponding to the first mode, and this is not to the scale. So just for visualization purpose. So at any particular instant, if the system is vibrating with the first natural frequency, it will be having the theta 1 and theta 2 will be having fixed ratio. So if it is coming in the other extreme, then also it will be following the same pattern. So even in the intermediate positions also, it will be having the same ratios. Okay, so next the second eigenvector. So eigenvector in the same, put the lambda 2 now. Lambda 2 and lambda 2 is having value 165.5. If we simplify this, we will get this matrix. If we take one of them, as we did in the previous, we can take second also, which will be getting the same value. So the ratio of the theta 2 and theta 1 becomes minus 2.63. So if we take theta 1 as 1, theta 2 will be having minus 263, so both are angles. So here, this I've tried to plot here. You can see theta 1 is, let us say, 1 unit. Theta 2 is negative, so that means it has to move in the other direction. So the solid line is representing how the two masses will be having motion. So if the first mass in the right side, second mass will be in the left side. When the first mass is coming in the left side, this will go that side. So it will be having that kind of so-called anti-phase motion. Anti-phase. So this is going right side. This is going in the left side. So this is called anti-phase motion. Previous was the in-phase motion. So first mass is going in one direction, same direction the second mass is also going, and simultaneously they are coming toward the other side. But in the second case, they are swapping their positions in the anti-phase mode. So these are the two eigenvector we have obtained. This is corresponding to the second eigenvalue. And as I mentioned, if we say theta 2 is 1, correspondingly theta 1 will be having other value. So both eigenvectors are valid the way we are normalized. Okay, so at present we are not normalized these eigenvectors with respect to the mass. So at present we are normalized so that we can visualize better the relative magnitude we can able to see. So these two eigenvector can be put in a matrix. So this is the first eigenvector, this second eigenvector. So this is corresponding to the first natural frequency. This is corresponding to the second natural frequency. So if we put the values of that, this will be the matrix. So this matrix is nothing but the U matrix, so-called U matrix, which we can able to use for transformation. So this U matrix, the model matrix, this is a model matrix. So if we see the previous things, if we post multiply this by this transformation matrix and pre-multiply by transpose of this. So this is the transpose of this U matrix, and this is a mass matrix. So if we multiply it, we will get a diagonal matrix. And this diagonal matrix I am representing as M11, M12. So at present, because we are not normalized the eigenvector with respect to the mass matrix, so we are getting a diagonal matrix having some values. If we normalize the eigenvector with respect to the mass matrix, so here this is the original matrix, and then M11's square root I'm dividing here, and this I'm dividing by M22. So if I put the values of this, so this is the resultant mass matrix, which is normalized with respect to mass. So I have represented this by a, in the cap there is a, so just to distinguish. So this is representing that this is the eigenvector which has been normalized with respect to the mass. So this is the mass normalized eigenvector. Now if you use that eigenvector or eigen model matrix again in the mass matrix, because we have normalized with respect to mass, if you multiply, we'll get an identity matrix. Now instead of M11, I'm writing this cap also, so that, so this is a mass normalized eigenvector is giving a identity matrix. If we multiply the K matrix with original matrix of the model matrix without normalization, we will get this kind of number, which I'll call as K11 and K22. Now the same thing if I normalize with respect to the, if we multiply with the normalize with respect to mass eigenvectors, so then if you multiply, you will get whatever the values you will get. If you remember, this was lambda 1 and this was lambda 2, which is nothing but omega 1 square and omega 2 square. Yes. So you can see the how the mass normalized model matrix gives directly the square of the natural frequency, the first and the second, and the natural frequency can be obtained by taking the square root of this quantity. Now the transformation which we defined from the natural coordinate to the other coordinate, I think this should be other way around. Theta 1, theta 2. Okay, this should be other way around. Is that? So theta should come here and eta should come here. I'll correct that and send it to you. So when we substitute the transformation matrix in the equation of motion in terms of the generalized coordinate, we'll get the equation of motion in the natural coordinate like this, with transform mass matrix is this and transform stiffness matrix is this. So in the previous case, we already seen when we are using general Eigen model matrix, we got the M11, M12 like this, and K11, K22 like this. So you can see that this equation of motion, earlier it was mass matrix was coupled, now it is uncoupled. Stiffness matrix was uncoupled, now still it is uncoupled. So that means if I expand these equations, I'll get two equations which are uncoupled equations. This is corresponding to the first mode. This is corresponding to the second mode. And individually this can be solved. And if we divide this through by this, I'll get this as the omega square 1. And if I divide this through this, I'll get this is lambda 2, which is nothing but the natural frequency square. So you can see this is a single degree of freedom equation where if I divide by mass, this will be the natural frequency square. Similarly for the second one. So these are the uncoupled equations which we are trying to find out so that the solutions of these equations are easier. So if we use the directly mass normalized transformation, which we obtain, so this equation of motion will be much simpler because mass matrix will become identity matrix, and the stiffness matrix will be square of the natural frequencies directly. So this will give us the square of natural. So this is the same equation when we divide the mass term, same thing here. Okay. So this is the equation of motion which we obtained earlier also. Okay. So if you want to solve this using Matlab, just 2 minutes, I will explain this. So the T matrix, if I'm defining K inverse into M, K matrix is this, M matrix is this, original matrices. So D matrix will be this. And then you need to take the eigenvalue and eigenvector of this directly. So this is the steps. So you define the K matrix. So K matrix is 30. So definition of this in the Matlab. So this is the K matrix. Similarly, mass matrix. So this is the mass matrix. This is a Matlab command. So if you want the D, which is K inverse M, so this is representing the K inverse. This is preferred. The backslash is preferred. So it's something like M is above the K. So the K inverse is this. Now to obtain the eigenvalue, eigenvector of this D matrix, this is the command. So Eigen EIG bracket D, and P will be the eigenvector, Q will be the eigenvalues. So you can see we got the eigenvector. So this is corresponding to the first mode. This is corresponding to the second mode. You can see these are both positive. Here one negative in the second mode. These are the eigenvectors, lambda 1, lambda 2. So in this lambda 1 and lambda 2 is defined other way around. I think 1 by lambda. So we need to invert this and take the square root of this. So if we take the inverse of q and take the square root, we'll get the first natural frequency and the second natural frequency. Then this is the normalization. So normalization of the eigenvector. So if I say this is 1, so you can see this value we obtained earlier. If I say this is 1, then second will be this. So this is the first eigenvector. This is the second one. Other way we can able to do here, we have done the m by k. If I do k by m, sometimes k matrix is singular, so we cannot able to invert the k matrix here. So sometimes we need to do k by m, where m is non-singular matrix. Then this is the A matrix. Eigenvalue of this we can get like this, eigenvector, and eigenvalue is this. So here you can see the eigenvalue is directly square of the natural frequency. So this we need to see. Here there is no need to invert while finding the natural frequency. So directly it can be obtained. Here you can see this is the first eigenvalue, eigenvector, but both are negative. So if I take this as 1, both will become positive, which will be same as this. And here also, if we take this as 1, it will come same as this. So same thing can be solved in the Scilab also. Only I think this red mark, rest is same. Only the command for the eigenvalue is different. Otherwise is same in the Scilab. And whatever the operations I did in the command mode, if you type this in a file, all the steps, and save the file with some name in Matlab, I think it should be .m extension. If I write this command directly onto the command mode, then all the things will be executed sequentially, and you'll get these answers directly. Whatever I have done by step, in the script, this is something like a code which you have done one by one. So this will be the display. Similarly, in the Scilab, I think only thing will be the extension will be SC instead of M. So the same answers you get from that also. So I'm stopping here. If you have any question, then you can ask. Any questions? Oh, yeah, Manpreet Singh.
Hello, sir. Good evening.
Hi, evening.
Yes, sir. Actually, I want to ask what are the natural coordinate in last problem we solved? As we know, generalized coordinate are theta1 and theta2. So, what are those natural coordinate? I mean, I'm not
natural coordinate. Yeah, natural coordinate is imaginary coordinates. Okay, these are the imaginary coordinate in which the equations are uncoupled.
Means we cannot pinpoint it on diagram like we said, like theta1, theta2 are the generalized coordinate.
So what is happening here when we are transforming the equation into natural coordinate, we are getting n number of single degree of freedom system. Okay. So they're independent of each other. So we cannot show the relative displacement of them.
Okay.
So these are imaginary coordinates where all the equations are uncoupled. So that means we have now n number of single degree of freedom system. Earlier we had single system and degree of freedom system.
Okay. Yes, sir.
Okay. One system and degree of freedom system. Now n system, all single degree of freedom system. So
yes, sir.
Okay. So
yeah, got it. Thank
you. Patel.
Yes, sir. Yes, sir. Hello, sir. I want to ask that. So, can you share the Saturday's lecture video because
video, no? I think
yes, Saturday's video recording.
Actually, is there in a particular? I think Pantha will share that thing. I think it's there in one place. I think he has not shared because of some reason. Pantha, can you tell something?
Sir, I have shared yesterday, sir. Actually, due to some internet reason, I could not share that day. I shared
Okay.
yesterday, sir.
Okay. I will check, sir.
But
And sir,
send me the link also, Pantha, so that I
Okay,
can.
yes, sir. Yes, sir. Yes, sir. I'll send now.
okay, sir, and about the assignment, you have said that we should get the uncoupled stiffness matrix.
Huh.
Sir, but I'm getting couple stiffness matrix, and if off diagonal elements are zero, then can we say that is a uncoupled?
Yes, off diagonal terms are zero, then it is uncoupled.
Okay, sir.
No.
Yes.
That means if you expand those equations, you will get equations independent of each other. Like
yes, sir. Yeah, got it.
Like today we got it.
Yes,
Today we
like
got it.
in one equation only one generalized coordinate will be there, in the second equation only second generalized coordinate will be there.
In this
Okay.
stiffness.
Yes, sir, got it.
Yeah.
Yes, sir. Thank you.
Yeah. So, okay, so I think I'll stop here then.